So imagine taking a solid rod of hardened steel, and we are talking 65 HRC here.
Right, which is just incredibly hard material.
Yeah, exactly.
Yeah.
It's material so hard that it practically deflects standard cutting tools.
Yeah.
And you take this steel and you just attack it with a ring of carbide blades spinning at like 8,000 RPM.
Which sounds completely insane.
Right, because physics basically dictates that doing that should immediately create this localized fireball of friction. I mean, you'd melt the metal, completely destroy the structural integrity of the part, and probably just shatter your tooling everywhere.
Oh, absolutely. Standard physics says that's exactly what should happen.
But today, for you listening, welcome to the deep dive. Because today we're looking at a manufacturing process that does exactly this, yet the metal barely rises above room temperature.
It's honestly kind of magical.
It really is. We're looking at this fascinating source document breaking down CNC whirling technology, specifically in ball screw manufacturing.
Right.
And it is just a complete masterclass in challenging those baseline assumptions of mechanical engineering. So, okay, let's unpack this.
Yeah, let's do it.
Our goal today is to extract the actual mechanisms here, the underlying physics and those logistical aha moments that allow this tech to take a stagnant, 50-day manufacturing bottleneck.
Yeah, up to 50 days in some cases.
Right, and compress that entire nightmare into a single long weekend. And we want to do this so you can apply these problem-solving insights to your own work.
Because it really is a complete subversion of traditional machining logic. I mean, to understand the magnitude of what CNC whirling actually accomplishes, we really have to look at the mechanical limitations of the traditional process first.
The baseline, right? The old way of doing things.
Exactly. The old way of cutting those deep Gothic arch threads into that hardened 65 HRC steel. Traditionally, you're relying on single proaxial cutting on a lathe.
Right, so that's basically taking a single cutting tool and just running it longitudinally down the rotating shaft over and over.
Yeah, pretty much. But because the steel is at maximum hardness and that Gothic arch profile is relatively deep, you run into this massive tool pressure problem.
Because you're pushing a single point against a really hard surface.
Exactly. If you try to cut too deep with a single point, the sheer resistance of the hardened steel will do one of two things. It'll either shatter the carbide insert completely, or it'll cause that massive, 8-meter shaft to just deflect away from the tool.
Oh, wow. So it just bends out of the way.
Right. So the only way to manage that radial pressure without breaking everything is to take these agonizingly shallow passes. I mean, you just scrape away a fraction of a millimeter, reset the machine, and run it all over again.
And the source notes this requires dozens of passes just to hit the final thread depth.
Dozens of passes. It is just incredibly inefficient. The tool is engaged constantly. The machine time is totally exorbitant. And your overall throughput is entirely bottlenecked by the physical limits of, single-point tool deflection.
So, okay, instead of dragging one blade back and forth across the part endlessly, CNC whirling introduces an entirely different geometry, right? The source describes this cutter ring holding multiple inserts that orbit the workpiece. Am I picturing this right?
Yeah, you're on the right track.
Like, if traditional turning is basically like slowly whittling away a stick with a single pocket knife, pass after pass, is CNC whirling like passing that same stick through a high-speed buzzsaw ring?
That is actually a really effective way to visualize it, but there is a crucial geometrical twist here.
Okay, what's the twist?
The orbit is eccentric, so the whirling head, which is that massive ring of carbide inserts you mentioned, is tilted. It's tilted to match the exact helix angle of the thread you're trying to cut.
Oh, I see. So it's angled right into the groove.
Exactly. And while that ring is spinning at up to 8,000 RPM, the spindle that's holding the steel rod is rotating very, very slowly in the same direction.
Meaning the cutting action isn't axial anymore. It's not just running straight down the line.
Correct. The inserts are cutting tangentially. Because you have multiple cutting edges engaging in really rapid succession, you're distributing that massive cutting load across the entire wing.
Rather than just one poor little tooltip.
Right. And because of this, the machine hits a milling speed of 400 meters per minute. Because those heavy cutting forces are dispersed tangentially rather than pushing radially against a single point, the whirling machine can carve out the entire depth of that Gothic arch thread in one continuous pass.
Just one pass. That is wild.
Depending on the pitch and the diameter, it operates, 5 to 30 times faster than a traditional lathe.
Okay, but here's where it gets really interesting for me. Because speed is great, obviously, but as we established at the top of the show, 8,000 RPM on hardened steel should absolutely trigger a thermodynamic nightmare.
Oh, it sounds like a recipe for disaster.
Right. If I am cutting that aggressively, where is all the heat going? Because with traditional grinding, the source specifically highlights thermal damage as this massive persistent failure point.
Yeah. And what's fascinating here is how whirling exploits chip formation to just bypass that thermal bottleneck entirely. Because you are totally right to point out the dangers of traditional grinding.
It just bakes the metal right.
It does. Grinding wheels don't just cut, they rub. You have millions of these tiny abrasive grains plowing through the steel, creating this sustained, intense friction. And because a grinding wheel is constantly engaged with a really large surface area of the thread, the heat has nowhere to go but directly into the workpiece.
Which leads to what the source called raceway annealing.
Precisely. The sustained heat literally undoes the heat treatment you just paid for. The steel in the raceway softens up, and then, as the metal rapidly heats and cools over and over, that thermal expansion and contraction tears the molecular lattice apart.
Oh.
Yeah, it creates these dangerous microcracks on the surface. It's what the industry refers to as white layer formation, and it completely compromises the load-bearing capacity of the final ball screw.
Okay, so if rubbing and sustained contact cause all that heat to soak into the part, how does the whirling ring avoid doing exactly the same thing? I mean, even at high speeds, those carbide inserts are still violently displacing hardened steel.
It really comes down to the mechanics of shear. Because of that eccentric orbit we talked about and the tangential entry angle, the whirling insert isn't actually plowing the metal like a grinder does.
So what is it doing?
It enters the material, reaches its maximum chip thickness almost instantly, and then cleanly shears off this tiny comma-shaped chip of metal right before exiting.
Wait, so the chip physically separates from the rod before the thermal energy even has time to conduct back into the main shaft?
Exactly.
It's like the chips are acting as tiny thermal escape pods or something.
Escape pods captures the physics perfectly. The shear action is so rapid. I mean, we are talking fractions of a millisecond of engagement per insert, that roughly 80% of the kinetic heat generated by the cut stays localized within that comma-shaped chip.
80%.
Yeah. And the chip is ejected instantly. So as a result, the temperature of the actual workpiece barely rises a few degrees above room temperature.
But hold on, if the chips are carrying all of that thermal energy, what happens to the carbide inserts themselves? Don't they just melt or degrade super rapidly under that kind of intense localized heat?
Well, they would if the heat actually lingered. But whirling is fundamentally an intermittent cutting process.
Meaning they get a break between cuts.
Right. An insert strikes the metal, generates the heat, ejects the chip, and then it spends the rest of its rotation just traveling through the air before its next strike. So it naturally air cools during that brief little transit.
Oh, that makes so much sense.
And the machine heavily utilizes compressed air, too. It blasts those searing hot comma chips away from the cutting zone immediately so they don't transfer heat back into the tool or the part.
Which is why this is a dry cutting process. You don't use fluids.
Yes. Flooding the zone with liquid coolant would actually be detrimental here.
Wait, really? Why?
Because coolant can cause thermal shock to the carbide inserts. It cools them too rapidly after the cut, which leads to microfractures in the tooling. So dry air blasting evacuates the chips cleanly without introducing thermal shock and without trapping abrasive grit against the newly cut thread.
Okay, so since we aren't using coolant and we're skipping the rough grinding wheel entirely, that has to completely change the surface condition of the final part. The source document notes that CNC whirling reliably delivers an immediate surface finish of raw 0.8 microns.
It does. It completely eliminates the need for rough grinding.
But what does this all mean for the end product, for the user? Because the source also points out that standard precision grinding can achieve a much smoother finish, right? Down to like raw 0.2 microns.
Yeah, much smoother.
So if we skip grinding to save all this time and we just settle for raw 0.8, aren't we basically just accepting a good enough surface, just trading quality for manufacturing speed?
You know, if we connect this to the bigger picture of tribology, which is the study of friction and lubrication, that is actually a really critical misconception. We are totally conditioned to assume that a perfect mirror-like finish is mechanically superior.
Right. Smoother is always better.
But in a high-load dynamic environment, a raw 0.2 surface is actually too smooth.
Too smooth? How can a surface be too smooth? How does that cause a failure?
It causes boundary lubrication failure. When heavy loads compress those steel ball bearings against the raceway, the lubricating oil needs somewhere to anchor itself. If the surface is just a flawless mirror, the extreme pressure simply squeezes the oil film completely out of the contact zone.
Oh, I see.
Yeah, so you get metal-on-metal contact. And that leads to galling, rapid wear, and eventually total failure.
So the raw .8 finish from the whirling process isn't a compromise at all. It's actually an engineered feature.
Exactly. Because those carbide inserts strike the metal intermittently, overlapping one after another, they leave behind a very specific microstructure. It basically flattens the peaks but retains these microscopic valleys.
And those valleys hold the oil.
Right. It creates what engineers call superior lubricant retention volume. Those tiny valleys act as micro reservoirs. So under pressure, the oil has a place to sit, maintaining that hydrodynamic film and drastically reducing operating friction.
This is a total paradigm shift. I mean, we usually associate perfectly smooth with highest quality, but here, a slightly textured, mechanically rougher finish is actually holding the oil better and outperforming the polished one. We were basically over-polishing our parts to their own detriment.
We really were. And it gets better because the source also mentions something called cold working.
All right, I wanted to ask about that. If grinding tears the metal away, what is the high-speed whirling process doing to the actual molecular structure of the steel?
This is perhaps the most significant metallurgical advantage of the whole thing. Grinding is an abrasive process, right? It tears the molecular lattice at the surface, which induces tensile stress.
And tensile stress is bad.
Very bad. Tensile stress pulls the surface apart, which invites cracks. Whirling, on the other hand, relies on those high-speed tangential impacts. When that carbide insert strikes the hardened steel at 8,000 RPM, it doesn't just cut it. The sheer force of the impact plastically deforms the surface boundary.
So it's actively compressing the grain structure of the steel. It's kind of like packing a snowball incredibly tight right at the very outer edge.
Yes, great analogy. That compression forces the molecular lattice tighter together. It induces what we call compressive residual stress, which is the exact opposite of what grinding does.
Because compressive stress pushes it together, resisting cracks.
Exactly. Compressive stress actively resists crack formation. It hardens the outer layer of the thread even further, and it does it without using any heat. So by replacing grinding with whirling, you avoid thermal microcracks, you optimize lubricant retention, and you actively strengthen the molecular surface of the thread.
The mechanical elegance of that is just striking. But okay, let's zoom out for a second and look at the whole factory floor. Because solving the physics is really only half the battle here. The source notes that the traditional manufacturing cycle for these components traps capital and labor in the factory for up to 50 days.
Yeah, the traditional supply chain for ball screws is a total logistical nightmare. It involves roughly 20 separate operations. First, you have to take the green or unhardened steel and rough cut a preliminary thread on a lathe.
Right, because it's too hard to cut at full depth once you bake it.
Precisely. So then you send that roughly threaded rod away for heat treatment to bring it up to that 65 HRC hardness. But heat treatment is a violent process. As the metal heats and quenches, the internal stresses release, causing the shaft to warp, stretch, and bend slightly.
Which means the thread you just spent all that time cutting is no longer perfectly straight or aligned.
Right. So when that warped shaft finally comes back to the factory, the operators have to perform these agonizing lead pickup operations.
What does that entail?
Well, a machinist has to manually probe the hardened, distorted thread and try to perfectly synchronize the CNC grinding wheel's path to match a thread pitch that has literally stretched inside a furnace.
Oh my God.
Yeah, and if they are off by a fraction of a millimeter, the grinding wheel just destroys the part.
And you have to do that across multiple slow grinding passes. It is no wonder it takes 2 months to finish one of these things. But because the whirling cutter is rugged enough to slice through 65 HRC directly, you basically completely invert that entire workflow.
You change the entire order of operations. You heat treat the raw, unthreaded bar stock first. Any warping or internal stress release happens before you ever even touch a cutting tool to the metal.
Wow.
And then, once the solid rod is hardened, you put it into the CNC whirling machine, and it carves the finished, perfectly pitched thread into the hard steel in one pass.
So you completely bypass that lead pickup nightmare because there's simply no pre-existing thread to align with.
Exactly. You eliminate rough turning, you eliminate lead pickup, and you eliminate rough grinding. One machine consolidates all of those setups. The manufacturing cycle drops from 50 days to between 1 and 3 days.
For anyone listening who manages projects or deals with supply chains, just imagine taking a 2-month bottleneck and doing it over a weekend. That is insane. But let me challenge the practicality of this for a moment. The text mentions these machines are handling shafts up to 8 meters long. If you take an 8-meter rod of steel, hold it at both ends, and assault the middle of it with an 8,000 RPM cutter. I mean, the harmonic resonance alone should cause the shaft to vibrate wildly. How does a machine moving that aggressively not just shatter the part into a useless piece of scrap?
That is a really important question about dynamic stability because all that speed and cutting force is completely useless if you can't control the deflection. Traditional lathes use steady rests, but they often sit too far back from the active cutting zone, which allows for micro vibrations.
Right.
The whirling machine solves this by using carbide follower rests.
How do those differ mechanically from a steady rest?
They grip the workpiece directly adjacent to the cutting ring. Think of them as incredibly rigid mechanical hands that travel with the tool, supporting the steel mere millimeters from where the inserts are actually striking the metal.
Oh, so it physically braces the cut.
Yeah, but mechanical support isn't enough on an 8-meter shaft. The system also relies heavily on dynamic CNC compensation.
Meaning the software is actively following the deflection in real time.
Yes. The machine's sensors monitor the exact position and sag of the shaft constantly. As the whirling head travels down that 8-meter length, the CNC software continuously micro-adjusts the X and Y axis of the cutter to perfectly counter the natural bowing of the metal.
That's brilliant.
Right, because the follower rests kill the physical vibration, and the computer constantly corrects the geometry, chatter marks are virtually eliminated.
And the proof is in the yield, honestly. The source notes the scrap rate drops below 0.3%. You're moving exponentially faster, but you're actually making fewer mistakes. And on top of all that, by eliminating the grinding phase entirely, you are completely removing toxic grinding swarf from your factory.
Swarf disposal is a massive hidden cost in traditional manufacturing. Grinding creates this awful, toxic slurry of metal particulate, shed, abrasive grit, and degraded liquid coolant.
Yeah, it's nasty stuff.
It's an environmental hazard. It is incredibly expensive to filter and dispose of, and it just coats the entire machine shop in grime.
Whereas the comma chips from the whirling process are just dry, clean steel.
Dry, clean, easily recyclable steel chips that just blow right into a bin. And instead of constantly dressing and replacing massive, expensive grinding wheels, you are using small carbide inserts. When an edge dulls, you just rotate it. When the insert is totally spent, you replace or resharpen it. The operational overhead shrinks dramatically.
So synthesizing everything we've pulled from this document today, CNC whirling isn't just a faster lathe. By switching from single-point radial scraping to multi-edge tangential shearing, the process basically circumvents the thermal limits of hardened steel entirely.
Absolutely.
It replaces a 50-day, 20-step logistical nightmare with a clean 3-day turnaround. It eliminates toxic waste. And ironically, by abandoning the pursuit of a flawless mirror finish, it utilizes cold working to create a micro-textured surface that literally holds oil better and structurally outperforms the parts we spent decades over polishing.
It forces us to reevaluate the very physics of our bottlenecks. I mean, we tolerated that 50-day cycle because we just assumed extreme hardness required extreme friction to shape. Whirling proves that if you change the geometry of the attack, you can bypass the friction entirely.
And that is the core takeaway for you listening right now. Look at the complex, traditional 20-step bottlenecks in your own industry or your own life. How many intricate lead pickup realignments are you performing just to compensate for a warped process upstream? Are you spending 2 months grinding away at a problem that a different geometry, a tangential cut, could slice through in a single pass?
And if we take this just a step further, it really challenges our fundamental design philosophies. I mean, if this mechanical cutting process proves that an imperfect, slightly textured surface is actually vastly superior at holding lubricant and reducing friction than a flawlessly polished one,
Yeah.
what other perfectly smooth, highly polished products or systems in our everyday life are actually structurally weaker purely because we are obsessed with how finished they look?